We all know that water is essential for the survival of all forms of life. It forms a major part of all living organisms. 60% of the human body is made up of water. And in some plants, this quantum goes up to 90%. Water covers 71% of the Earth's surface. However, the distribution of water over the Earth's surface is not uniform. Oceans contain 97.33% of water on the Earth's surface. Only 2% of water on the Earth's surface is in the form of polar ice and glaciers. The remaining water, less than 1%, is present in lakes, rivers, in the atmosphere, and as underground water. Let us now look at some physical properties of water. Water is a tasteless and odorless liquid at standard temperature and pressure. It freezes into ice at 273 Kelvin. Its boiling point is 373 Kelvin and has a density of 1 gram per cubic centimeter at 298 Kelvin. Water has strong hydrogen bonding in its molecules and, therefore, exists as associated molecules. Due to the presence of extensive hydrogen bonding in its molecules, water has a high freezing point, a high boiling point, a high heat of vaporization, and a high heat of fusion in comparison to hydrides formed from other group 16 elements, like H2S and H2SE. In comparison to other liquids, water has high thermal conductivity, surface tension, dipole moment, and dielectric constant respectively. And also, it has highest specific heat. These properties allow water to play a key role in the biosphere. Its high heat of vaporization and high heat capacities are responsible for the moderation of the climate and the body temperature of all living beings. Water is an excellent solvent for the transportation of ions and molecules required for animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds such as alcohol, and carbohydrates dissolve in water. The shape of water molecule is bent or V-shape with a bond angle of 104.5 degrees and OH bond length of 95.7 picometers. In water molecule, as the oxygen atom has a higher electronegativity than hydrogen atom, it carries a partial negative charge, whereas the hydrogen atom carries slightly positive charge. As a result, water is a polar covalent molecule. In the liquid phase, water molecules are associated by hydrogen bonds. The crystalline form of water is ice. At normal atmospheric pressure, ice crystallizes in hexagonal form. The density of ice is 0.9167 gram per centimeter cube at 273 Kelvin, whereas water has a density of 0.9998 gram per centimeter cube at the same temperature. In winter, The frozen ice on surface of the lakes provides thermal insulation and is important for the survival of aquatic life. Ice has highly ordered three-dimensional hydrogen-bonded structure, in which every oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 picometers. Hydrogen bonding gives ice a rather open crystal lattice structure with wide spaces between the molecules. These vacant spaces can hold some other molecules of appropriate size interstitially. Chemically, water reacts with large number of substances. Let us look at some of these reactions. Amphoteric nature. Water is amphoteric in nature, which means that it can act as an acid as well as a base. According to the Lowry-Bronsted concept, water can act as an acid by losing a proton and as a base by accepting a proton. For example, in the reaction with ammonia, water acts as an acid by giving H+ ion and forming NH4+ ion. In the reactions with hydrogen chloride and hydrogen sulfide, water behaves as a base by accepting H+ ions and forming H3O+ ions. Water also undergoes autoprotolysis or self-ionization, in which one molecule of water acts as acid 1 and another molecule as base 2 to give a molecule of acid 2 and base 1. These are also known as conjugate acid and conjugate base. Redox reactions involving water. Water can easily be reduced into hydrogen by highly electropositive metals. For example, sodium metal reacts with water to give sodium hydroxide and hydrogen. Therefore, it is a great source of hydrogen. Water is oxidized to oxygen during photosynthesis. The reaction that takes place is 6 molecules of carbon dioxide react with 12 molecules of water to give 1 molecule of glucose, 6 molecules of water and 6 molecules of oxygen. It also reacts with fluorine gas to give oxygen and ozone. Hydrolysis reactions. Water is a strong solvent and dissolves many ionic compounds. However, due to its high dielectric constant, it has very strong hydrating tendency and can easily hydrolyze many ionic and covalent compounds. Water hydrolyzes the oxides and halides of nonmetals to their respective acids. For example, it hydrolyzes phosphorus pentoxide to give orthophosphoric acid. It also hydrolyzes silicon tetrachloride to hydrochloric acid and silicon dioxide. Water also hydrolyzes the carbides, hydrides and nitrides of some metals. For example, it hydrolyzes both calcium carbide and aluminium nitride to give ethine and ammonia respectively. The reactions that takes place are: calcium carbide reacts with water to give calcium hydroxide and ethine. Water reacts with aluminium nitride to give aluminium hydroxide and ammonia. Hydrate formation. Many salts can be crystallized as hydrated salts from their aqueous solutions. There are three types of hydrates. The first type of hydrate is coordinated water. For example, in Cr H2O6 3 plus 3Cl minus, water molecules are coordinated to metal ions in a complex. The second type of hydrates is interstitial water. For example, in BaCl2 2H2O, water molecules occupy interstitial sites in the crystal lattice. In the third type of hydrates, water molecules are hydrogen bonded to certain oxygen-containing anions. For example, in CuSO4 5H2O, one water molecule is hydrogen bonded to sulfate ion, and the other four molecules are coordinated to give CuH2O4 2- plus SO4 2 H2O. Water is classified as soft and hard depending on the type of dissolved salts and behavior with soap. Soft water produces lather easily with soap and contains no calcium or magnesium ions. A good example of soft water is rainwater. Hard water, on the other hand, does not produce lather with soap easily and cannot be used for laundry. For example, river, sea, and sometimes even well water. The hardness of water is due to the dissolved salts, like bicarbonates, chlorides and sulfates of calcium and magnesium ions. When rainwater makes its way through the ground, it dissolves the salts of calcium and magnesium and turns hard. Let's see why hard water cannot be used for laundry. Hard water contains calcium and magnesium cations, which react with soap to form scum or precipitate of calcium and magnesium salts or fatty acids. Laundry soap contains sodium stearate. When sodium stearate reacts with the calcium and magnesium salts, it forms calcium and magnesium stearate precipitate. Until all the calcium and magnesium ions are precipitated, lather is not produced. This is why hard water is unsuitable for laundry. Hard water is also harmful for the boilers because of the deposition of salts in the form of scales, which reduces the working efficiency of the boilers. Hardness of water can be classified as temporary hardness and permanent hardness. Temporary hardness of water is due to the presence of soluble calcium and magnesium hydrogen carbonates, respectively. There are two common methods to remove temporary hardness. The first method is boiling. Hard water is taken in a large boiler. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium carbonate, while calcium hydrogen carbonate changes to insoluble calcium carbonate. The precipitates of magnesium carbonate and calcium carbonate are removed by filtration, leaving soft water as the filtrate. The second method to remove temporary hardness is known as Clark's method. In this method, a calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Permanent hardness is due to the presence of salts of magnesium and calcium in the form of chlorides and sulfates. Permanent hardness cannot be removed by boiling. It is removed by other methods, which include treatment with washing soda, Kalgin's method, ion exchange method, synthetic resins method. Let us look at each of these methods in detail. Treatment with washing soda or sodium carbonate. A calculated amount of washing soda is added to hard water. Washing soda reacts with the soluble chlorides and sulfates of calcium and magnesium in hard water to form insoluble carbonates. The second method of removing permanent hardness is Kalgin's method. In this method, calcium and magnesium ions are not removed from the water, but are rendered ineffective by the addition of sodium hexametaphosphate, commercially called Kalgin. Calcium and magnesium ions react with Kalgin to form a soluble complex. The complex anion keeps the magnesium and calcium ions in solution, not allowing them to react with soap. In ion exchange method, also called the zeolite or permutate process, hydrated sodium aluminium silicate or zeolite, when added to hard water, exchanges cations such as magnesium and calcium ions for sodium ions. For simplicity, sodium aluminium silicate NaAlSiO4 is written as NaZ. Once all the sodium in the zeolite is used up, it is regenerated for further use by treating with an aqueous sodium chloride solution. The fourth method of removing permanent hardness is the synthetic resins method. In this method, synthetic cation exchanges are used. This method is more efficient than the zeolite method. Cation exchange resins contain larger organic molecules with groups such as SO3H or COOH that are water insoluble. They exchange their H+ ions with the cations in hard water. Anion exchange resins contain organic molecules with groups such as NH3OH that exchange their OH- ions with the anions present in hard water. Pure demineralized or deionized water, free from all soluble mineral salts, is obtained by passing hard water successively through a cation exchange in the H+ form and an anion exchange resin in the OH- form. In the cation exchange process, the H+ ions in RCOO-H+ are exchanged with sodium, calcium and magnesium ions present in the hard water. The reaction that takes place is RCOOH in solid state plus M2+ in aqueous solution gives MrCOO taken twice plus 2H+ ions in aqueous solution, where M+2 is a calcium or magnesium cation. Since this reaction releases H+ ions, it makes water acidic. In the anion exchange process, RNH2 in water gives RNH3 plus OH-. The OH- ion in RnH3 plus OH minus gets exchanged with chloride, bicarbonate and sulfate anions present in the water. The reaction that takes place in RnH3 plus OH minus reacts with X minus to give RnH3 plus X minus and OH minus ions, if X is chloride ion. The released OH minus ions neutralize H plus ions. Once the cation and anion exchange resin beds are exhausted, they are regenerated by treatment with dilute acid and alkali solutions respectively.